Welcome everybody once again. So today in Canny's method, let us see how to analyze a portal frame with the sides way. And the difference of this problem from the previous problem is that today we are going to analyze a portal frame with sides way having vertical loading and columns are of unequal height. So you can see A, B and C, D are the two columns of the portal frame. The height is AB, the column AB is of height 3 meter and the column CD is of height 2 meter. It is subjected to a vertical load, vertical UDL, vertical uniformly distributed load of 6 kilonewton per meter over the span BC. So let us see how to analyze such problem. Okay, so as usual, first step we are going to find the fixed end moment. So we know fixed end moment. Our assumption is we assume all the supports are fixed. So since we are assuming all the supports are fixed, the left you will have hogging moments at the supports. So since it is hogging moments, since the moment is hogging, we will have anti-clockwise moment at the left support and clockwise moment at the right support. Because when you take this section, left anti-clockwise is negative and right clockwise is negative. Okay, so clockwise we will consider it as negative and anti-clockwise we will consider as positive. So the moment is negative, right? The moment when we take about the section is negative, both the supports. So for anti-clockwise we will give negative sign and for clockwise we give positive sign, and the values are for fixed end moment. It has, since it is UDL, for an UDL it is minus WL square by 12 and plus WL square by 12 at the right support. Now, for the span AB, there is no any external loadings. Therefore, M of AB is equal to M of BA is equal to 0. M of BC is equal to minus WL square by 12. We get minus 6 into 2 square by 12. 2 is the distance of the span BC. So, we get minus 2 kilonewton meter. MFCB, CB is equal to plus WL square by 12. We get plus 6 into 2 square by 12 plus 2 kilonewton meter. And, oh, I forgot to write one step. Okay, also MF, we will consider the column CD. When we are considering the column CD, MFCD is equal to MFDC is equal to 0. Now, step 2, we will find the rotational factors. So, we know rotational factor is equal to minus half of the distribution factor. Minus half of the distribution factor. Distribution factor is K by sigma K. So, first of all, we will consider the joints. So, we have joint B and C where more than one member acts. So, we will consider joint B and C. At B, we have the joints, we have the members BA and BC. At C, we have the members CB and CD. So, at B, so joint B, we have the members BA and BC. So, stiffness factor. How we know stiffness factor, if the far end is fixed, the stiffness factor is I by L. Relative stiffness, okay, this is nothing but relative stiffness is I by L, and if the far end is hinged, the relative stiffness is 3 by 4 I by L. Here, everywhere it is fixed. A is fixed, D is fixed, B and C are intermediate supports, so they are also considered to be fixed. So, everywhere it is I by L. So, this is a relative stiffness. Relative stiffness represented by K is I by L is equal to, for the member BA, I is given as 2I. For BA, I is given as 2I. L is 3 meter. So, 2I by L is 3. For member BC, I by L, I is given as I and L is 2. So, Similarly, for the joined C, we have the members CB and CD. For CB, the relative stiffness is I by L. So, it is equal to I by 2. For CD, the relative stiffness is I by L. Again, for CD also, it is I by 2 because for CD, I is given as I. So, we will take the summation of the stiffness at joint B and joint C. At joint B, summation 2I by 3 plus I by 2 is equal to 7I by 6. At joint C, I by 2 plus I by 2 is I. Now, distribution factor is equal to K by sigma K. So, 2I by 3 divided by 7I by 6, we get 4 by 7. Similarly, I by 2 divided by 7I by 6, we get 3 by 7. Here, I by 2 by I, we get 1 by 2. I by 2 by I, we get 1 by 2. See, distribution factor is K by sigma K. Here, the coefficient is equal to 1, right? That means, when you add these both, you should get 1. When you add the distribution factor at joint C, we will get the summation equal to 1. Now, rotation factor is equal to minus 0.5 into K by sigma K. So, minus 0.5 into 4.7, we get minus 0.2857. For member BC, minus 0.5 into 3 by 7, we get minus 0.2143. For CB, it is minus 0.5 into 1 by 2, we get minus 0.25. And for CD also minus 0.25. Now, see here you can see the rotation factor, the coefficient is minus 0.5. You add these both, we get minus 0.5, and the rotation factor for at joint B, we get minus 0.5. Okay, once after finding the rotation factor for the frames subjected to sideway using Canny's method, we have to find a displacement factor also, because there will be rotational contribution corresponding to rotation factor and displacement contribution with respect to the distribution factor. So, we have obtained the rotation factor. Now, we will find what is the distribution factor. Now, displacement factor. So, displacement factor for frames having columns of unequal height and vertical loadings. So, we have to take this condition. The third condition which we have studied in the previous classes. So, unequal height and vertical loadings. If the frames have unequal height and vertical loadings, the displacement contribution is given by m dash of ij is equal to dij. So, dij is displacement factor into mr. That means restrained moment in that particular column. I told you earlier, displacement is with respect to column. So, if you have A, B, C, D, displacement is with respect to the column AB and the column CD. So, MR means the moment of this column, right? Plus sigma R, the summation of all the columns of the particular story into Cij into Mij plus Mji. Mij means it is MBA plus MAB. Similarly, Mji means MCD plus MDC. Now, Cij is called reduction factor. Okay, Cij, we will see that Cij is called the reduction factor. Before that, the displacement factor Dij will be equal to minus 1.5 into Cij Kij by sigma R. R means story level. Okay, here we have only one story. So, the first story into M into Cij square into Kij. So, we know what is Kij, right? The unknown things are Dij, M and Cij are new here. So, M is equal to 3 by 4 for hinged columns and 1 for fixed columns. For our case, it is fixed column. So, our M is equal to 1. Suppose if the column has hinged support, then we will take M is equal to 3 by 4. Now, DBA, D means Dij. Wait. Dij means the displacement factor. Okay. Dij is the displacement factor. So, displacement factor is equal to minus 1.5. We know this is the formula, right? So, now minus 1.5 Cij. Here I is B and J is A. So CBA, KBA divided by sigma R. M is taken as 1. Okay. M is equal to 1. Now sigma R Cij square Kij means we have two columns, right? So it is for the column, for the first column, that is for the column BA, this is equal to CBA. CBA square KBA plus CD square KCD. So that is equal to minus 1.5. See, this is for the first story. R means for the first story. This is, we have two columns in the first story, BA and CD. Okay, so this means for the column BA and for the column CD, summation of the column BA and CD. Okay, so minus 1.5 into CBA KBA by CBA square KBA plus CCD square KCD. We will substitute the values. CBA is equal to 3 by 3. Why CBA is equal to 3 by 3? So this is called CBA. Cij is called reduction factor. We saw this in the last class, previous classes. This is called a reduction factor. So that is equal to the reference length of column by length of column considered. Now, here our span is like this, right? A, B, C, D. So, AB is of span 3 meter, CD is of span 2 meter. So, we will take AB as the reference span. AB as the reference column. So, if AB is the reference column, CBA will be equal to length of the reference column is 3, length of the column considered is 3. That is why it is 3 by 3. Similarly, for CCD, CCD will be equal to reference column length is 3 because reference column is AB. So, reference column length is 3. The column to be considered CD is 2. So, it is 3 by 2. Here you can see it is 3 by 2. Okay. So, other things we have found earlier. So, we get which is equal to minus 0.5581. So, CD is equal to 3 by 2. Similarly, our DCD will be equal to minus 1.5 CCD KCD divided by CCD square KCD plus C. So, this is a summation of the two columns. By CBA square KBA. So, we get minus 1.5 into CCD is 3 by 2. Okay, we have found here. This is 3 by 2 multiplied by KCD. Relative stiffness of CD is I by 2. So it is I by 2 divided by 3 by 2 the whole square into I by 2 plus 3 by 3 the whole square into 2I by 3. We get minus 0.6279. So see here the factor is minus 1.5. So if you add these two, adding these two, you get minus 1.5. No. Sorry, this will not. This condition is not satisfying here. Okay, so for displacement factor, you need not consider that. Now, for the next step, finding the resultant restrained moment. So, at joint B, first of all, at joint B, this is for joint B, the resultant restrained moment is MFB is equal to the fixed end moments, the summation of the fixed end moments at joint B. So, MFBA plus MFBC is equal to minus 2 kilonewton meter. And at joint C, MFC, resultant restrained moment at C is equal to summation of all the fixed end moment meeting at C. So, MFCB plus MFCD, we get plus 2 kilonewton meter. Now, step 5, we will draw the Canny's iteration cycle. Okay. Okay. So, while drawing the Canny's iteration cycle, we have two joints B and C. So, this is joint B and joint C. We have the columns BA. So, this is the column BA and CD. Now, inside the smaller column, we will write the resultant restrained moment. So, at B, the resultant restrained moment is minus 2 and at C, the resultant restrained moment is plus 2. Now, we will write the fixed end moments. So, we know fixed end moment for AB is 0, fixed end moment for BA is 0, fixed end moment for BC is minus 2, fixed end moment for CB is plus 2, fixed end moment for CD is 0, fixed end moment for DC is 0. Now, we will write the rotation factor and displacement factor. So, the rotation factor for at joint B, the rotation factor is for BC, it is 0.2143. I think minus, right? So, everywhere the rotation factor is minus. Okay. So, it is minus 0.2143 minus 0.2143. The rotation factor for BA. For BA, the rotation factor is minus 0.2857. The rotation factor for CB is minus 0.25 and the rotation factor for CD is minus 0.25. Now, we will write the displacement factor. So, the displacement factor, we will write inside a box. Okay. So the displacement factor is for the columns. For the column BA, the displacement factor is minus 0.5581 and the displacement factor for the column CD is minus 0.6279. Minus 0.6279. Now we will write the rotational contribution and displacement contributions. So we know rotation factor is for at joint B and at joint C. So we will have M, B, C, M, B, A. Rotational contributions at joint B. Rotation contribution at joint C is M, C, B and M, C, D. Similarly, the displacement contributions are the displacement contribution for the column AB. So, AB and BA is same. So, we will write it as M dash of BA and here displacement contribution for the column CD, that is M dash of CD. M dash of CD is the same as M dash of DC. Okay. So now we have to find these contributions, displacement contributions and rotational contributions. So for that we will open up the tabular column called Canny's iteration. So the rotational contributions and displacement contributions. So at joint B we have rotational contribution and displacement contributions. At joint C we have rotational contribution and displacement contributions. So first of all at joint B, first of all we will find the rotational contributions. Then we will move on to displacement contributions. So rotational contributions are MBA at joint B, MBA and MBC. Here this RBA and RBC remains the same always, right? So it is the rotational factor multiplied by the restrained moment plus the rotational contribution from the neighboring support. Okay, rotational contribution from the neighboring joints plus displacement contribution from the neighboring column. Rotational contribution from the neighboring support, displacement contribution from the neighboring columns. So here RBA is always the same, that is not going to change. So RBA is minus 0.2857. The restrained moment at B is also always the same. So here it is minus 2.0, minus 2. Initially, the rotational contributions can be taken as a 0 for the first iteration. Because we don't know what is MAB and MCB, so that can be considered as a 0. We don't know what is M dash of BA also, so that also can be taken as 0. So these values changes for every step. Okay. So here it is. Okay. Now, see what is MAB? So from joint A, the rotational contribution is 0 at joint A. So every time this MAB is 0. We don't have rotational contribution at joint A. So MAB becomes 0. Only these two things changes for every iteration. MCB and M dash of BA changes for every iteration. Here, when you take MBC, rotational factor RBC is minus 0.2143. Minus 0.2143. MFB is minus 2. Same, okay. So the values inside the bracket remains the same. So initially we take these both as 0. So we get minus 0.2857 multiplied by minus 2. We get MBA is equal to plus 0.571. Now MBC is equal to minus 0.2143 multiplied by minus 2, we get plus 0.429. Now we will move on to the rotational contribution at joint C. So the rotational contribution at joint C is the rotational factor for CB multiplied by the restraint moment at joint C plus the rotational contribution from the neighboring joints. So when you take C, D, B, A, the neighboring joints are B and D. So it is MBC plus MDC. Plus at joint C, the displacement contribution from the neighboring column. Here the neighboring column is CD. So the rotational contribution is from CD, that is M dash of CD. Okay. So similarly, MCD will be equal to rotational contribution RCD into MFC. Remaining things are same. MBC plus MDC plus M dash of CD. So here also RCB remains the same. So what is RCB? Rotational contribution CB is minus 0.25. So minus 0.25 and RCD is minus 0.25. MFC is plus 2. MFC is plus 2. MBC changes for every iterations. So MDC is always equal to 0. So these values changes. Initially we don't know what is M dash of CD. So we can take this as a 0. MBC. For the first iteration, MBC, we have already found MBC is plus 0.429. So you have to take this value plus 0.429. So what we get is minus 0.25 multiplied by plus 2 plus MBC is plus 0.429. M dash of CD, initially we can take it as 0. We get MCB as minus 0.607. Similarly, MCD is also equal to, so because there is no change in the values, it is equal to minus 0.607. Now we will move on for displacement contributions. So displacement contribution, the formula is M dash of Ij for vertical loadings and columns with a different heights are Dij into sigma r Cij into Mij plus Mji. So first of all, for the joint B, we have the column BA. So M dash of BA is equal to DBA into summation of this, right? Summation of this. So Ij is BA. So CBA into for the column BA. That means we have two columns. See, at story R, that is we have only one story. At R we have two columns BA and CD. So this is for the column BA and this is for column CD. So summation of Cij into Mij plus Mji for the column BA. CCD into MCD plus MDC for the column CD. So what we get is, so DBA remains the same. DBA is equal to minus 0.5581. Minus 0.5581. CBA, we have already found CBA is equal to 1. Right? 3 by 3, that is equal to 1. CCD is equal to 3 by 2. CCD is 3 by 2. Reduction factors. Right? We have found these values while finding the displacement contributions. Now, MBA, MAB, MCD and MDC should be obtained from the previous iterations. So, here M dash of BA is equal to minus 0.5581 multiplied by 1 into MBA. So, MBA we have found it as plus 0.571. So, 0.571 plus MAB. We don't have rotational contribution at the support A, at the joint A. So, MAB is always equal to 0. Same way MDC is always equal to 0. So, we get into plus 3 by 2 multiplied by MCD. MCD is minus 0.607. Minus 0.607. So, we get the displacement contribution for the joint B for the column BC. Sorry, BA. At joint B, the column is BA. That is equal to plus 0.189. Similarly, for the joint C, we have the column CD. So, the displacement contribution is similarly same formula as for joint B. So, DCD into, this is the same, right? So, CBA into MBA plus MAB plus CCD into MCD plus MDC. So, what we get is DCD, distribution contribution for the column CD. Distribution factor for the column CD is minus 0.6279. Minus 0.6279. CBA, see the remaining things are same. CBA is 1, MAB is always equal to 0, CCD is 3 by 2, MDC is always equal to 0. So, what we get is minus 0.6279 multiplied by 1 into 0.571 plus 3 by 2 into minus 0.607. So, we get M dash of CD for the first iteration. M dash of CD is equal to plus 0.213. Now, we will move on to the second iteration. Iteration 2. So, for the second iteration, MBA is equal to RBA remains the same, that is minus 0.2857 multiplied by MFB also same minus 2. MAB is always 0. MCB In the previous iterations, we obtained it as minus 0.607. So, minus 0.607 plus m dash of BA, we have obtained m dash of BA as plus 0.189 plus 0.189. So, we get for the second iteration, we get MBA is equal to plus 0.691. Now, iteration 2 for MBC. MBC, we get similarly, see same values for MCB and m dash of BA. MCB is minus 0.607, m dash of BA is plus 0.189. So, we get MBC, the value for MBC is plus 0.518. Now, we have to find the rotational contribution at the joint C. So, rotational contribution at the joint C is minus 0.25 into plus 2. MBC, we have obtained in the last iteration, MBC, the value is plus 0.518. Plus 0.518. M dash of CD, we have obtained M dash of CD as plus 0.213. Plus 0.213. So, we get MCB is equal to minus 0.683. MCB and MCD is also same. So, we get minus 0.683. Now, displacement contribution. Displacement contribution, first of all, we will consider for joint B. For joint B, the displacement contribution is minus 0.5581 multiplied by 1 into MBA. MBA, for the last iterations, we obtained MBA as plus 0.691. 0.691 plus CCD is 3 by 2 multiplied by MCD. MCD is minus 0.683. Minus 0.683. So, we get the displacement factor MBA, M dash of BA is equal to plus 0.186. Similarly, the rotational contribution, displacement contribution M dash CD, you can substitute the values which you have obtained in the last iterations. For MBA and MCD, what you have obtained in the last iteration, you use the values, you will get M dash of CD is equal to plus 0.209. Similarly, you can continue for iteration 3 cycles, iterations 3, 4 and 5. Okay. So, find the values. So, complete the iterations. I will write you the values. So, first is for MBA, right? MBA, MBC, M dash of BA, MCB, MCD, M dash of CD. Okay. So, the values are for MBA, for the third cycle, MBA is equal to plus 0.713. MBC is equal to plus 0.535. Iteration 4, MBA is equal to plus 0.717. Sorry. Yes, MBA is equal to plus, right, plus 0.717. MBC is equal to plus 0.538. For the fifth iteration, MBA is equal to plus 0.718 and MBC is equal to plus 0.538. Now, the rotational contributions for MCB. For third iteration, MCB is equal to minus 0.686. Here both are same, so minus 0.686. For the fourth iteration, minus 0.684, minus 0.684. For the fifth iteration, minus 0.683, minus 0.683. Now the displacement contributions for the third iteration, the displacement contribution is plus 0.186. M dash CD is, sorry, for the third iteration, M dash BA is plus 0.176 and here it is plus 0.198. Fourth iteration, M dash of BA is equal to plus 0.172 and M dash of CD is equal to plus 0.194. For the fifth iteration, M dash of BA is equal to plus 0.171, M dash of CD is equal to plus 0.192. So these are our values. See, these values has to be considered for the rotational, and the values in the column iteration 5 should be used for obtaining the final moments for rotational contribution and displacement contribution. Now we will write these values in the iteration cycle. Okay. So let us write the values. We will move on to iteration cycle. Okay. So first of all, we will write for MBC. MBC, the values are plus 0.429, plus 0.518, plus 0.535, plus 0.538 and plus 0.538. For MBA, the values are plus 0.571, plus 0.691, plus 0.713, plus 0.717, plus 0.718. Now, the rotational contribution MCB is equal to minus 0.607, minus 0.683, minus 0.686, minus 0.684, minus 0.683. Rotational contribution MCD minus 0.607, same, okay, minus 0.683, minus 0.686, minus 0.684, minus 0.683. Now the displacement contributions M dash BA is equal to, displacement contribution M dash BA is equal to plus 0.571, plus 0.691, plus 0.713, plus 0.717, plus 0.718. For M dash of CD, it is minus 0.607, minus 0.683, minus 0.686, minus 0.684 and minus 0.683. So we will move on to step 7, right? So step 7, we will write the rotational and displacement contributions. So rotational contributions, MBA is equal to the last iteration, the value you have obtained in the last iteration. You have to consider the value which you have obtained in the last iteration. So the values are MBA is equal to plus 0.718, MBC is equal to plus 0.538, MCB is equal to minus 0.683, MCD is equal to minus 0.683, M dash of BA is equal to M dash of AB is equal to, here for displacement contribution, M dash of BA is equal to M dash of AB. It is for column, not for joints, it is for columns. Is equal to plus 0.718, and M dash of CD is equal to M dash of DC is equal to minus 0.683. Now we will use these values for finding our final moments. So we will take that as step 8. Step 8 is determination of final moments. So for determination of final moments, we know the Scanis method is an extension of slope deflection equation. So we know the moment MAB, final moment MAB will be equal to MFAB plus 2 into 2EI by L, 2EI by L into 2 theta A plus theta B minus 3 delta by L. Actually, this theta A is AB, theta B is BA, and delta is AB. So what we get is MAB is equal to MF of AB plus 2 MAB plus MBA plus M dash of AB. Because 6EI del into delta A by 6EI delta minus 6EI delta AB by L square is taken as M dash AB. So in general form we get MIJ is equal to MF of IJ plus 2MIJ plus MJI plus M dash of IJ. Now we will open up the tabular column. So we have MIJ is MF of IJ, 2MIJ, MJI, M dash of IJ. Here MIJ is equal to MF of IJ plus 2MIJ plus MJI plus M dash of IJ. So our members are, we have the members as MAB, MBA, MBC, MCB, MCD, and MDC. Okay. So we already know MFIJ, that is MAB is 0, MBA is 0, MBC is minus 2, MCB is plus 2, MCD, M of CD is 0, 0. Now 2MIJ, that is MAB, 2MAB. We don't have 2MAB, right? That is MAB is equal to 0 because fixed ends there is no rotational rotation factor and rotational contribution. Similarly, MDC also equal to 0. So 2MAB is equal to 0. 2MBA is equal to plus 0.718 into 2. MBA plus 0.718 multiplied by 2 we get plus 1.436. Now 2MBC. BC it is plus 0.538. So plus 0.538 divided by 2. We get plus BC plus 1.076. Here MCB is minus 0.683. So 2 into minus 0.683. MCD, small MCD, right? Minus 0.683. So 2 into minus 0.683. MDC is 0. Now MJI. MJI means it is for the member BA. So MBA is plus 0.718. 0.718. MAB is 0. MCB. MCB is minus 0.683. Now MBC. MBC is plus 0.538. MCD minus 0.683. MCD MCD is 0. MDC is 0. MCD is minus 0.683. M dash of IJ means M dash of AB, right? M dash of AB, M dash of BA, etc. So M dash of for AB and BA, BA and AB it is plus 0.718. For BC and CB it is 0. For CD and DC minus 0.683. From which we get MAB is equal to, add all 0 plus 0 plus 0.718 plus 0.718. Is the 0.718? What is M? BA is also 0.718. Huh? See, I think there is some mistake here, right? See, this is wrong actually. See, I put the same value. So the values are m dash BA is equal to plus 0.189 plus 0.186 plus 0.176 plus 0.172 plus 0.171. Similarly, here it is plus 0.213 plus 0.209 plus 0.198 plus 0.194 plus 0.192. So I made a mistake here. Here the values are plus 0.171 and plus 0.192. So it is plus 0.171, 0.171. Here the values are plus 0.192, plus 0.192, plus 0.192. Okay. So adding adding all this, we get 0 plus 0 plus 0.718 plus 0.171. We get plus 0.889. So adding all this, we get MBA is equal to plus 1.607. MBC is equal to minus 1.607. MCB is equal to plus 1.172. MCD is equal to minus 1.174. MDC is equal to minus 0.491. So everywhere it is kilonewton meter. So how will we draw our bending moment diagram? For the span AB, so AB it is positive, so clockwise, right? Pointing towards the right. BA also clockwise. So our bending moment diagram will be like this. For the span BC, anti-clockwise and clockwise. So the bending moment diagram will be like this. For the span CD, this anti-clockwise, anti-clockwise. So it is like this, right? Pointing towards the right, at a D pointing towards the left. So now we will draw the bending moment diagram. So for AB, first of all we will draw the simple beam moment diagram. So for simple beam moment diagram, for the span BC, M max is equal to WL square by 8. So we get 6 into 2 square divided by 8. We get 3 kilonewton meter. So this is 3 kilonewton meter. Now we will draw the beam moment, the final end moment diagram. So here it is pointing towards the right? The value is 0.889. Here it is pointing towards the left, 1.607. Here it is upwards, 1.607. Here also upwards, 1.173. Here it is pointing towards the right, 1.173. Pointing towards the left, 0.491. So our net bending moment diagram is okay. This is our net bending moment diagram. So from this, when we draw the deflection diagram, so drawing the deflection diagram is 1.607, 1.173. So this will move towards here. Okay, and we will have the deformation like this. The span BC will be deforming like this. So here we will have a point of contraflexion at this point and another point of contraflexion at this point. Now, at this point we have a point of contraflexion. So here the deflection is like this. At this, almost at this point we have a point of contraflexion, and here the deflection is like this. So we will have a point of contraflexion at this point. So this is our deflection diagram. This is the bending moment diagram. So with this we have completed our fourth module. From the next class we will move on to our next module. So thank you for listening.